We have a question on fluid mechanics from IIT 2005, and the question has a system with 3 beakers which is filled with liquid. They are connected to each other, so all of them are filled to the same level L, and then the whole thing is rotated about arm B. It acts like a centrifuge at an angular speed omega, and the question is, what should be the value for omega so that the level of liquid in the arm B goes to 0? Okay, so try and solve this yourself by pausing the video. Okay, time to solve it. What we'll do is, we'll first look at a little simpler system, a system with just 2 arms, basically a U-tube. We'll rotate that, and let's see how to take care of the centrifugal acceleration in the rotating reference frame. So imagine I have a U-tube which is filled with some sort of a liquid. Let's say the liquid is, let's take it as water itself. The liquid will be to the same level in both the arms. Okay, let's call this distance as some L, and let's now rotate the whole thing at an angular speed omega about this arm. Let's call it as arm A, and this is arm B. Well, what's going to happen now is that every single particle in the fluid is going to experience an acceleration, and that acceleration will be towards the center. Centripetal acceleration is what it's going to experience. So the fluid is no longer in equilibrium, and therefore our hydrostatic equations don't work because it's not in equilibrium. And that's going to be a little bit complicated for us. So to make sure the liquid stays in equilibrium, there is a method to that, and that is going into rotating reference frame. So let's enter into the rotating reference frame of the liquid itself. Rotating reference frame. Basically, imagine someone is sitting on this tube and trying to solve and trying to analyze. In the rotating reference frame, we are going to assume that the U-tube is at rest. And you can always do that. And the moment you do that, you realize that you are inside a non-inertial reference frame. Okay? So we are going to assume that this whole U-tube is at rest. And if that were to happen, then we have to take care of pseudo forces. And the pseudo force is centrifugal force, or pseudo acceleration is centrifugal acceleration, and that acceleration is always away from the center, or from the away from the axis of rotation. So it's going to be this way. So this will be the direction of the centrifugal acceleration. Okay, this acceleration pretty much acts like fake gravity. So in the rotating reference frame, this pseudo acceleration is going to do everything that any normal gravitational field does. Okay, here if we went back to our fluids and we went back to lab reference frame, and for a while let's forget about rotation, and if I picked any 2 points in the fluid over here, so let's call this point as P and let's call this point as Q, you know that the pressure at Q is higher than the pressure at P because there exists a gravitational field downwards. Therefore, this column is going to exert a force, and therefore there's a pressure difference. However, there is absolutely no difference in the pressure between point Q and say point S if they're at the same level, because there's absolutely no gravitational field in the horizontal direction. Well, that's when things are not rotating. But once we are in the rotating reference frame, things change. Not only do we have a gravitational field acting downwards, but we also have an extra fake gravity in the horizontal direction, in this case towards the right. So the same effect happens. So now if I choose any 2 points in the liquid, say I choose a point here and point here, let's call this as point A and point B, then just like how Q is at a higher pressure than P, B has to be at a higher pressure than A because of the fake gravity. So pressure at B has to be higher than the pressure at A. Okay, so if that is true in the rotating reference frame, that must also be true in the lab reference frame. It has to be true. So even when I look at it from lab reference frame, I must somehow conclude that the pressure at this point must be higher than the pressure at this point because of rotation. But in the lab reference frame, I ask myself, what causes that difference in the pressure? I mean, in reality, there is no gravitational field in the horizontal, right? Ooh, the only way that can happen is if the height of this fluid were a little bit raised and the height of this fluid was a little bit lowered down. So you know what would happen? Because of this, there will be a difference in the height created. I hope you can now conceptually understand what is the effect of rotation. It causes a height difference because it causes a pressure difference. So the only way a pressure difference can be created is if this were to go. Another way to think about it is, think of it this way. Notice that if these 2 points are at the same pressure, that's what happens initially, then this fake gravity pushes liquids towards the right, at least seen from the rotating reference frame, pushes liquids towards the right, and that causes the liquid over here to rise and the liquid over here to drop. It keeps on pushing until the weight is too much, and eventually the pushing force, the fake pushing force, the pseudo force, is exactly countered by the real gravity. Okay, I hope that makes sense to you. So that causes the height difference, and what I want to figure out is what is this height difference? I mean, the height difference must depend on certain things like the density of the fluid. Maybe it must definitely depend upon the angular speed omega, because if omega is 0, h should be 0. So I want to calculate what's the connection between h and omega. That's going to help us solve that IIT problem. Okay, to do that calculation, we need to find out an equation for the pressure difference along this horizontal because of the fake gravity. Now you might be inclined to say, why can't we use the same particular equation as we used in hydrostatics? We can say pressure at the bottom is the pressure at the top plus rho g h, and g is that fake gravity. Can't we just do that? Well, no, we can't do that because this gravitational field is not uniform. The gravitational field at point A is almost 0, it's along the axis, and as you move farther and farther away, the gravitational field keeps increasing. The fake gravitational field keeps increasing. So we cannot take care of it. We cannot do this directly. So what we'll do is, we will pick a random point, a random section of the fluid over here, which I have marked. Let's take that section to be dx, and I will zoom that in over here. This is what I've taken, a section of the fluid. That section is dx. And let's say the mass of that section of the fluid is dm. And since there is a gravitational fake gravity acting this direction, this side over here must be at a lower pressure compared to this side. This side must be at a higher pressure. Okay, so there should be some small difference in the pressure, an extremely small difference in the pressure, because of this I've taken a differential length, and let's calculate that difference in the pressure. So how do we calculate the difference in the pressure? Well, the difference in the pressure must be exactly equal to the force, the pseudo force that's acting on this, right? Does that make sense? Must be exactly the equal to the pressure due to the pseudo force. Okay, so I can write that dp, that's the difference in the pressure, to be exactly equal to the pseudo force cos divided by the acceleration. I hope that makes sense to you. A very, very tiny pseudo force acting on a tiny piece over here, pseudo force df, and that pseudo force equal to the mass of this section, that is dm, times the acceleration at that point. Now what's the acceleration over here? Let's call this distance as x. I actually forgot to mention that is x. This is dx, this is x. Then the acceleration at that point will be omega squared times x divided by a. Now as x value changes, as the x value keeps changing, the dp will also keep changing because the acceleration keeps changing. Can you see that? As x value increases, dp keeps increasing. So to calculate what the pressure difference here is, I need to integrate this equation. But to integrate that, I need to take care of this dm. So what I'm going to do is, I'm going to divide and multiply by dx. So I'll take dx in the denominator and numerator. And the reason is, a times dx, a is the area, it's this cross-sectional area, it's this area. And dx is this length, so that a times dx represents the small volume, and dm divided by that small volume is going to represent the density. So dp can now be written as density rho, that represents this part, times omega square x dx. And now we are ready for integration. So if we integrate this, we now get the difference in the pressure between these 2 points. So I'm going to integrate it from pressure at A to pressure at B, and that's going to be the integral of omega square x dx from x equal to 0 to x equal to some length L. Alright, let's do this integration. This will give me PB minus PA, and rho comes out, omega square comes out, and we have x squared by 2, that becomes L square divided by 2. So we now have an equation for PB minus PA. That's equation number 1. But we can calculate PB minus PA in another way. We can do that from the lab reference frame, and from the lab reference frame we can say, well, there is no fake gravity. So what's causing the difference in the pressure? Ooh, that's due to the difference in the height. That's what's causing the difference in the pressure. Okay, so by the way, I hope you understand the difference in the pressure here is the same as the difference in the pressure here. Anywhere is the same. Anyways, the pressure difference is caused due to the difference in the height, and that's why you have a higher pressure over here. So we can use now hydrostatic equation that we are familiar with. We can use this equation, but along the vertical now. And so we can now say PB minus PA should also be equal to rho g h. H is the height difference that you're getting over here. It's this extra column that's causing that extra pressure. So rho g h is the pressure due to this extra column. So this is equation number 2. Equate 1 and 2 and we get rho g h equals rho omega square L square divided by 2. Rho cancels. And we now have h equals omega square L square divided by 2g. Ta-da! That's the value for height. Okay, now that we understand what's going on, let's go back and solve that problem, shall we? And we have to assume that the cross-sectional area is very tiny. Very, very tiny. So this cross-sectional area is very small compared to L. So this is also L. Okay, so you can think of them as extremely thin tubes. And now it's rotated about point B. Arm B. Okay, so clearly we can now understand what's going to happen. The same thing that we learned earlier is going to happen over here. There's going to be centrifugal acceleration this way from the rotating reference frame. So if I go back to rotating reference frame, redraw that. Alright, so in the rotating reference frame there's going to be a centrifugal acceleration this way and a centrifugal acceleration this way. That's going to cause this point and this point to be at a higher pressure compared to this point. Higher pressure over here. Okay, and that's going to make sure that the fluid over here drops and the fluid starts climbing up over here. And we need to figure out what should be the value for omega. What should be the value for omega so that all the fluid disappears over here and the fluid appears over here. That's what we need to figure out. So all the fluid disappears from there. Okay, so we have been given what the height difference is in this problem. So can we figure out what the height difference is going to be? Well, notice initially the length was L. Now another L amount of column gets added not only to one side but to the other side. So L by 2 gets added on either side. I hope that makes sense. Because this thing drops down and these two levels go up, L amount of fluid is removed from here and given. And since situation is symmetric about the axis, half the amount of liquid goes here and the rest half goes over there. And because of this, the new length is going to be L plus L by 2, and that's going to be 3L by 2. The new length over here is also going to be 3L by 2. And rest everything is going to remain the same. The physics is going to be exactly the same. So I might as well use the equation that I already derived. And the equation we derived was h equals omega square L square divided by 2g. That was the value for h. Now we already know what h should be, and in our example h should be equal to the height difference between this and this level and this level, and that's 3L divided by 2. And notice the cross-sectional area is negligible, so don't worry about whether the length is from here to here or from here to here. The cross-sectional area is negligible. So h equals 3L by 2. Let's substitute that over here. 3L divided by 2 equals omega square L squared divided by 2G. 2 cancels, and therefore we now have the required value for omega. Omega is going to be, L cancels, you will have 3G divided by L, the square root of that. Bingo, there we have it. That's the answer. That's the required speed for omega. So beautiful problem. I'll see you next time. Take care.